Physics and Astronomy Department, the public, and especially those who made all this possible, the Willard L. Eccles Charitable Foundation and the Catherine W. and Ezekiel R. Dumke Foundation. I am Professor Gondolo. I am the director of the High Energy Astrophysics Institute, and today we will have a series of presentations of the history of the change from the physics department to the addition of astronomy. Upstairs you can find images of the construction of the observatory on the monitors, as well as pictures that have been taken of the sky with the observatory in the first days. We tried to set up a live feed from Frisco Peak, and we have the connection up to campus, but we have trouble from campus to this department. So if we succeed in setting it up, it will also be visible upstairs in the monitor in the center. Otherwise, Wenspringer will have some images of the observatory. After the presentations, about 5 p.m., we have a reception which is open to everybody, and it is just upstairs here when you came in. And after the reception, about 6 p.m., the observatory on the south physics roof will be open for everybody. We cannot control the weather, but if it's still cloudy at that time, you can still look at the telescopes we have here on campus. So without further ado, let me introduce the chairman of the Department of Physics and Astronomy, Professor David Kieda, who will give us an overview of the history, how we came to where we are.
Okay, thank you, Paulo. Can everybody hear me from this? Okay. Okay, so what I want to do today is talk a little bit about history, and I hope, there we go, some good lights in here. I'm reminded of a story of a chairman of a department, faculty member, and a graduate student who are traveling a long way, perhaps down to Frisco Peak Observatory, and they're stopped by on the road by some bandits, and the bandits say, well, you know, we're gonna kill you guys, but everybody gets a wish. And so, of course, the chairman of the department says, oh, well, I've been working on this plan for the department for the last 5 years, and I really want to tell somebody about this plan to grow the department and make it much better. So I want to give a talk about this, so at least I can, you know, complete that work. And so it's okay, you can do that. And then the professor says, well, I've been working on this new theory for the last 5 years. I haven't told anybody, but I want to give an hour lecture on that. And is that okay? And the guy says, okay, sure. Then asked the graduate student what he wants. He says, kill me first. So okay, I hope it won't be that long. But what I thought I'd talk about is a little retrospective on the astronomy and astrophysics program. And so my outline, I'm going to start a long, long time ago, and then move on to A New Hope. I think this is a little familiar. And then talk about how a new astrophysics program was born. And in general, just like the universe, you can usually trace something that's born back to a single point in time or a single place. And for this astronomy program, it goes back a very long way. Perhaps back to 1964, one of our distinguished professors, Jack Koifel, he was the first one in the physics department to start moving on from doing some sort of solid state work. He worked in a mine underground, and he was looking at neutrinos from various astrophysical objects. So this was back in 1964, and that's Jack, and this is Haven Bergeson, also an emeritus faculty member from our department. And they built this experiment called the University of Utah Neutrino Experiment. This was actually in Park City. A lot of people don't even know about this. But there was a lot of astrophysics research being done in our backyard, even in the 1960s. And with this, they actually even imaged the Wasatch Front in high-energy muons that were created by particles going through the rock underground. So they actually had an image at one point of the Wasatch Front. Later on, just above ground at the at the same location in Park City, they started to do some optical observations, and they were looking at cosmic rays and particles as they would give off flashes of light in the sky. This is something called the nitrogen fluorescence technique, and one of the reasons they wanted to do this here is the fact that Utah has very beautiful skies. It's a very dark place, very clear weather usually, even in Park City, it's not too bad. This is a picture from George Cassidy, one of our professors in the department, and he said that they took about a 1 acre plot in Park City. This was about 1973, I believe they were doing this, and he said he wished they'd hung on to it because it would have been worth a lot more money now. Anyway, this is what the electronics look like, a bunch of cables. There's a very old oscilloscope, and they set up 3 mirrors here, and they actually saw particles, emitting something called nitrogen fluorescence, and from that they were able to figure out the distance to this particle and the energy of that event. So this was not exactly astronomy, this is considered to be astrophysics, but we were using the atmospheric skies. This eventually this Silver King neutrino detector led to a very, very large experiment called the Fly's Eye detector, which began operation in the late 1980s. It started, or actually late 1970s it started, and later on a subsequent detector called the High Resolution Fly's Eye came on just as I was coming on board as a faculty member. About 1988 I became on board when he first proposed this experiment. Later on there were other particle detectors that were created, something called the Casa-Mia array. These are arrays of particle detectors that saw particles coming from the sky and tried to look for point sources of detectors. But there was no real astronomy program up until even the year 2000. We were just doing cosmic rays. It was an internationally recognized program, but it's felt a shame that we couldn't actually use the fact that the night sky is incredibly dark. Here's a picture of the entire United States in 2000. And if you notice, the only real dark spot over here is in Utah. Most of the country has way too much light to astronomy, even including down here in Tucson, Arizona, out in Big Bend over here, out in California. That's where most of the major astronomical facilities are located in the United States. But they're located near urban centers, and there's a lot of light associated with that. So we started, a bunch of us in the physics department started thinking about what would it take to build an astronomy program and try to exploit these skies in southern Utah. And we were approached by the Eccles Foundation, amazingly, right about this time, and they're looking to do something new and actually looking to do something associated with astronomy. And so they gave us a small grant in 2000 to build the South Physics Observatory, which, again, you're welcome to come visit us after the snacks and everything. And this shows a picture of the observatory, a couple telescopes here. There's a bunch of them that are used for teaching courses. And with the observatory, we have star parties every night, but we also developed an astronomy minor program. We just developed upper undergraduate and even graduate level courses in astronomy. So based upon that South Physics Observatory, that brought a new hope to the department for actually building this astronomy program. We built these core courses in observational astronomy, cosmology, stellar structure, and evolution. And by 2006, we had an astronomy minor program here at the University of Utah. Based on our success, Steve came back a few years later and asked, what's your next plan? How do you want to grow this astronomy program? And so we asked him to give us the funding for a new telescope at the end of the year. We put in a proposal for it. This led to a couple other things. Once it was approved, a faculty search, and then later on it was mentioned Sloan Digital Sky Survey, and most recently we changed our name only a few months ago to the Department of Physics and Astronomy, sort of completing the whole process, at least the initial part of the process. As I mentioned, the reason why we wanted to come here was, here's the southern Utah sky. This was actually taken by Dan DeRisco. He's a park ranger in Bryce Canyon National Park. He monitors the night sky and see how beautiful the night sky here is in Utah. There's no light pollution really in the center of Utah, very high altitudes, large areas, last of the U.S. locations suitable for research astronomy. I also work at Kit Peak, and this is what Kit Peak looks like on a normal night. You see a sky glow from Phoenix and as well as from Tucson, and it's quite a bit different. We're much better than they are. So this is a proposal. March 2006, this was a drawing by the daughters of one of our faculty members, Lucy LeBowick. She drew that as just sort of getting excited about building a telescope. And a month later, the Eccles Foundation funded the proposal. And so it was up to us to actually make this thing happen. It's one of these blessings and a curse. We actually have got the money. Now we actually have to build this thing. And it's quite a job to do that. Wayne Springer will talk about that. You've probably seen some of the recent newspaper stories. Here's one that was just only a few days ago. University of Utah is building a brand new telescope. This is one of the first pictures of the assembled telescope. But not only did the Eccles Foundation help to get that going, a year and a half later they helped us out to join a major astronomical survey called the Sloan Digital Sky Survey. And here's a newspaper article regarding that. So Carl Dawson, another one of our faculty members, will talk about that in a minute. Perhaps I will end just talking about the fact that some of the main reasons we do this astronomy is for our undergraduates. We want to have a program which brings students into doing research. We have research experiences for undergraduates here in the department, and so those of you who have younger students and or younger young kids at home, if you wanted to think about in the future bringing them to the University of Utah, you can participate in world-class astronomy research here at the University of Utah. This is actually a group of students that I led over the past few years. I've been doing a summer research program at the Whipple Observatory in Tucson here. And these students here actually built these 4 monster telescopes. You can see this is a car down here. So these things are gigantic. By developing our program here at the University of Utah, we prepare students to work on world-class facilities as well as use world-class facilities here in the state of Utah. So our new astronomy program, 6 new astronomy faculty and counting. We have new telescope facilities, Southern Physics Observatory, Starbase Utah is another one. I won't even have time to talk about that one. That's in Grantsville, 35 miles away from here. The Eccles Observatory, Veritas Observatory, institutional affiliation with major astronomical instruments, Veritas and Sloan, undergraduate research opportunities for summer and academic year. And so in the end, I'd like to say thanks to Steve and to also the Dumke Foundation, Zeke, for providing us with the funding. I think this is a great picture. This was this past summer when we first broke ground, and it's very fitting because it shows exactly what's gone on here in the physics department in the last 15 years. A bunch of faculty members working together with our foundation to establish something new. Thank you.
Okay, can everyone hear me? I have a very soft voice. I'm suppressing the southern accent. My name is Wayne Springer. I'm the Associate Professor of Physics and Astronomy, and I have 48 slides to get through in 10 minutes now. Basically, I'll be talking about what several of us did on our summer vacation. I'll mention some things about why we built an observatory at Frisco Peak. Then I'll go through and show you some pictures concerning the construction and the installation of the telescope, and then some really, really nice photographs from the first and second nights of operation. I'll mention a few things about what we plan to do with it, and then I want to take some time to thank some people who were quite helpful. So Dave has already shown this picture of the skies above Arches National Park. I think this picture right here answers the question, why would you want to build an observatory in southern Utah? So I won't belabor that point. So in 2007, myself and 2 other undergraduate students, Paul Ricketts, who's still here, and another student who is now at Brookhaven National Lab, went and explored southern Utah and basically made measurements of how much the North Star twinkles from various sites to figure out where should we place this observatory. After about a year and a half of study, we decided on locating the observatory at Frisco Peak. And the reasons for doing so is that Frisco Peak is a very dark sky site, like some other sites we looked at in southern Utah. However, as you go to the west, you actually get to an even drier climate. So this was one of the driving elements toward moving it to Frisco Peak. We made about a year and a half worth of measurements and determined that the seeing conditions were excellent on Frisco Peak in spite of the wind. There were some practical reasons why we went to Frisco Peak. There's a, quote, road. There was an existing electrical power line, and as of last Thursday, that power line has been extended 660 feet down the ridge to our site, and we now have power. Today, personnel from the Utah Education Network were supposed to go up and install a microwave link. I don't know if they're going to be able to get that done before the weather sets in. And then probably one of the really good reasons for going there is the existence of Penny's Diner. It's open 24 hours a day. Here's Chris Zimmer, who is actually jumping for joy on Boulder Mountain. I guess he was excited to leave Torrey and fine restaurants known as El Diablo and head toward Penny's Diner. So this decision was taken in the summer of 2008. We submitted paperwork to the BLM July 2008, and slightly less than a year later, we were given the right-of-way. So, as Dave already showed, Frisco Peak is in a dark sky location. This map shows you the precipitation amounts across the state of Utah, and actually Frisco Peak gets about half as much precipitation as some of these other sites we were looking at. The measurements indicate that Frisco Peak has better seeing conditions, even though it doesn't have the best food. Boulder Highway is about 25 miles from El Diablo, this fine restaurant in Torrey, but unfortunately, the conditions weren't good there. Frisco Peak has an existing road. It's fairly steep. There's a couple of rocky spots. This is the top of the existing road, and right here is the beginning of our new road. You go up over a little summit. You can have fun with people when you take them up there for the first time. Here is the Department of Technology Services Radio Shack, where we're going to be putting some networking equipment. We're going to be mounting a 4-foot diameter microwave dish on this tower here. Fortunately, these facilities did not cause any problem with the telescope. I put about $3,800 worth of shields on the cables for the control system to make sure that that was not a problem. So the day after the migratory birds flew the coop from Frisco Peak, we had groundbreaking. Here is a picture of the ceremony. And the reason why I'm smiling, I don't smile too often, is that I didn't get a flat tire on the way up that day. Later that same day, real groundbreaking occurred. The mini excavator made its way to the site before there was a road. So one of the first things we had to do was to determine the soil conditions of the site. So the mini excavator took a few bites, and the professional geologist shown here then determined that the site was full of rocks. And then we designed the dome support structure accordingly. Shown here is the beginning of the new extension of the road. This is probably the more realistic speed limit. This one up here is a joke. A couple of days after this, we ruined the road. We had to put a trench in to get conduits for optical fiber and power. Many people wonder, how in the world do you get stuff up the mountain? Well, basically, you use flatbed trucks. The concrete was transported up in buckets. Unfortunately, I don't have a picture of the concrete truck. Dualies are not a very good vehicle for this road. The rocks get stuck between the two wheels and slice tires. The contractor and the subcontractors got about 11 flats during this construction phase. This device here is a 50-foot extension boom forklift, which works incredibly well for installing observatories. I just couldn't resist putting my now famous Isuzu Rodeo. It's appeared on KSL TV. This is the observatory staff transport. It's now climbed about 25 vertical miles in the past 2 months. I should give appreciation to Harold Simpson. He was the one who suggested these tires. This truck has not gotten any flats on the way up. One of the critical things was doing the survey work. When you're building a telescope, it should point, the mount needs to be pointed in the right direction, namely north. So Harold Simpson was really essential for designing some of the basic dome support structure elements, at least speccing it out, as well as helping with doing a lot of the survey work. And then I called in the big gun, Stan Thomas, who has this device right here. It's known as an azimuth gyro. It can align itself to north by using a gyroscope to better than 1 arc minute. And this is a little joke for those of you who know calculus and vectors. So the site survey, as prepared by the second engineering company, is shown here. One of the things I learned, I always wondered why you had to pay so much money for title insurance. Sometimes surveyors can be off. The original survey was off by about 110 feet. So shown here is where the dome is going to be, it is now located, and where the control room is located. So moving along quickly, about as quickly as construction progressed, I'll show a few construction slides. So here you see the form for the pier. Actually, Jeff Jacobson is in the audience. He was the job superintendent who, how many flats did you get personally? 15, okay. So here is the pier, and then here is a fellow who's played a very vital role, Paul Ricketts, who is taking a picture from the top of the dome, which you can see right here. So this facility is located right adjacent to about a 4,500-foot drop. And what you see out here is the Great Basin. There's really not much. On the road out to Frisco Peak, you pass a sign that says next service is 86 miles. So you got to go through that. So some more construction shots. Here is a picture of the pier and these pipes. It is through these pipes that we have all of the cables that go to the telescope and all of the instruments that will go in there. Basically, all of this intelligence will reside, or does reside, in the control room. And now there is a control room built around this. The dome was put here, and the telescope, of course, goes on top of that pier. So here is the dome support structure, which was built in a matter of a couple of weeks. The dome went up in about a week. It was very interesting for the construction workers. They had a very nice view. This is the view from the scaffold. It's a pretty long ways down. Here is a picture of the control room under construction. And you know, a lot of CEOs get a lot of bad press. Here's the Chief Executive Officer of Utah Commercial Contractors. Very, very impressive company. And then here is the nearly final version of the dome and control room. The control room now is painted in the same dreary olive drab color as the dome. Most of you would probably wonder, why in the world would you paint an observatory dome that color? And the answer is because we had to. Visual impact. We mixed in some infrared reflecting pigment to try to reduce the heating, but we'll see. We can do some things to mitigate. And then here are some pictures from the telescope installation. Here's the boom forklift hoisting in the pedestal mount, the primary mirror in its box. This is Richard Neal, the machinist from DFM, who actually machined most of the part, well, oversaw the fabrication of the telescope parts. And then here is the nearly completed telescope with the cables shown here coming out of the front end instead of where they ended up. And then here was a picture of the telescope installers during a relaxing moment overlooking the Great Basin. I believe this was just slightly after the telescope installation was complete. And then here's what most of you are probably most interested in. This image is the first image obtained from the telescope. Paul Ricketts and I were with the telescope installers, and we just looked at the planetarium software and said, okay, let's look at a galaxy near the zenith. We didn't know what it was going to look like, but we sure lucked out and happened on a nice one. What happened here? Okay. If you look really closely, you can see a few smudges. Those smudges are more distant galaxies. This galaxy is about 24 million light years away. It is a fairly dim galaxy, about 10.8 magnitude. But the thing that's really amazing about Frisco Peak is that you can see this through an eyepiece with your own eye. So those of you who have any experience looking at deep sky objects, you'd be amazed at what you can see from Frisco Peak. So that was an image from the first night. The second night I said, Paul, go have some fun. Go get some PR shots. Try to get as many things as you could get. So on the second night, he obtained 34 images of deep sky objects that sort of look like this. This is the Veil Nebula, and you can see that the seeing was fairly good that night. I'm not too sure if we had the focus perfect that night. The Horsehead Nebula, a galaxy cluster, another galaxy cluster in Pegasus. I encourage you to look on the internet for pictures of some of these things. I did, and these rival the best pictures that I've seen on the internet. You might wonder why they're in black and white. We were having problems with the filters the first night. This is a galaxy cluster in Perseus. The Ring Nebula. The Helix Nebula. Okay, it's a good thing Paul's here. The Crab Nebula. M81, is that right? This is an image taken through a finder scope and a Canon Rebel. The finder scope is just a simple refractor with no correction, so that's why you see these little purple circles around some of the images. That's a result of chromatic aberration. Makes a sort of an artistic effect as well. Nebula. Paul has placed images of the 34 objects at this website if you're interested in downloading them. Paul put the high resolution versions on there soon. The second half of the web page, no, the second third of the web page, fourth. Not a bad night. Okay, so it's pretty difficult to get up there. One of the things that we're really working hard on doing is to get the site to work remotely from here. What you see here is an image of 6 surveillance cameras. If the network was working right now, I could have this for you live. Maybe I can get it in a minute, but if you can see the site, you can see if there are problems. So this is a very crucial step to being able to run remotely, and that's already been done. Ideally, at least I would like to send a surrogate up there, a real, fully functional, human-like robot. You should see the movie Surrogates. It's kind of weird. It shows you what I would like to have. Or we could hire Calvin to design a robot. So what next? Like I just mentioned, we need to develop remote operation capability. Several of us have submitted a proposal to the NSF requesting funds to further develop that. We need to incorporate the facility into our courses and outreach activities. We're on our way toward doing that. One of the things that I really want to start focusing on, and some of our colleagues have started doing this, is to identify scientific research topics that we can use this facility for. Maybe this site is a really good site and we might want to put, or someone may want to put additional instruments up there, so we want to characterize the site. And I'm pretty tenacious, and I was really impressed with the site and the facility, and I want to get up there all year round. So my wife might find a charge for $3,395 to buy mat tracks for that rodeo. Some of the science topics that are possible are outlined in this report prepared by this committee called RESTAR, and it actually is a rather phenomenal list of topics that can be addressed with a 32-inch scope, especially when located at a place like Frisco Peak. We have pending proposals to the NSF. I've mentioned the one for developing remote operation capabilities. We also have a joint proposal with UVU, Joe Jensen and Carl Heisch, I believe. And this is made possible by our friends at the Willard Eccles Charitable Foundation, Steve, Scott, and Bill, the Dumpke Foundation, and the University of Utah Office of the Vice President for Research has contributed some funds for instrumentation. The College of Science, Dean, has been supportive. And then a special thanks, at least I want to get it on the record. It's usually a terrible thing to single out people for thanks because you're going to forget people. I know that I've done that already. But Paul Ricketts, I really want to convey thanks to him. Harold Simpson was essential. I had a lot of help from people in the Cosmic Ray group. John Matthews lent me vehicles. Some of them were kind of difficult to get up the mountain, but they were helpful nonetheless. The secretarial staff, Heidi, the accounting staff who had to deal with the receipts for several $100,000s worth of stuff. The list goes on and on. Utah Commercial Contractors, Jeff Jacobson. He's a guy who, I guess I could say, literally suffered to get this to work. Hunt Electric, the telescope manufacturer, the dome manufacturer, although the guys from the dome manufacturer left me a nice little present Paul found out the other night. The Bureau of Land Management, the Cedar City Field Office, has some really great people to work with. Beaver County, the Economic Development Director, Rob Adams, he was the guy who led, I believe, Paolo and I up to the top of Frisco Peak. CHPC has contributed some networking equipment. UEN is working on establishing the microwave link. Campus Design and Construction protected my butt in dealing with contractors, but it looked like I didn't need that much protection. Rocky Mountain Power finally came through with power last Thursday. Penny's Diner, Oak Tree Inn. If you ever need wireless connections in southern Utah, it's Alltel. Although they're going out, they're being absorbed by AT&T. And then finally, I'd like to thank my family, who has had to tolerate a little bit of absence on my part. Some web links, and then, as I've been quoted, I'm excited, exuberant, and somewhat exhausted.
Okay, so how is my mic working? Okay, so Wayne gave a presentation on one part of our new expansion in astronomy and more traditional astronomy research, and that's more facility development, a facility both for research and for educational resources and outreach. I'm going to talk about another branch of the development, and that is institutional collaboration, specifically the Sloan Digital Sky Survey. So in this talk, I'm going to talk about a brief overview of the Sloan Digital Sky Survey, its history. It started about 10 years ago. I'm going to talk about why they want to enter the next generation, what's the next generation of the Sloan Digital Sky Survey, and why the University of Utah and the Department of Physics and Astronomy decided to join, and what the advantage of doing so are. And then I'll give a brief teaser of the interests of the new astronomy faculty with respect to Sloan, the same faculty that Paolo just introduced. Okay, so the Sloan Digital Sky Survey. Here's a picture of the telescope on the left-hand side and a map where you can find it in New Mexico. It's about 2 hours from El Paso in the southeast corner of the state. And this goes back to about 2000, as I'll show on the next slide. It's a large collaboration of scientists from all different institutions from all over the world. Currently in this incarnation, there's about 20 to 25 different universities involved. It's located in southeastern New Mexico. It's on a mountain about 9,200 feet above sea level, so it's actually comparable height to the site that Wayne just described. However, there's different advantages to either place. This is closer to, this is a more well-established facility. It has a history that goes back 50 years with the Air Force and other organizations, but I don't believe the weather is as good as what we're seeing in southern Utah, and I also think there's more light pollution. It's a dedicated 2.5 meter telescope. So that's about 8 feet in diameter. And by dedicated, I mean all it does is observations for the Sloan Digital Sky Survey. So everything is scheduled years in advance. It's not a shared resource. It's not, you're not applying for time as an individual. And in the original version, there's basically two special purpose cameras. So by a telescope, the telescope is just the mirror. It's like the lens of a camera. You still have to build the light collecting element. And there's all different methods of doing so. The two particular ones that we chose for the Sloan Digital Sky Survey was an imager, which is an optical, very similar to what is on the back of a camera, like you buy a digital camera in the store nowadays. And the other is a spectrograph, which basically serves the same purpose as running light through a prism, like on the Pink Floyd album. Okay, so it began in 2000, and for about 5 years, it did a joint survey in the imaging camera and with the spectrographic camera. The imaging camera covered about a quarter of the sky. So the sky is 40,000 square degrees. It covered about 10,000 square degrees of that. At the same time, basically on alternating nights, it followed up in spectroscopy. And by spectroscopy, I mean, again, running through a prism, and by that you can get, running the light through a prism, by that you can get basically distances. You get a distance measurement to the galaxies. You get what's called a redshift measurement. It basically gives you a 3D distribution of objects in the sky. And that was targeting basically everything that was bright in the sky. So back then, the only purpose was to collect data. There wasn't a specific science case in mind. It was, we want to image the sky, we want to get spectroscopy in the sky. It's basically everything that's bright, everything we can get in this amount of time we're going to do. So in the 10 years since, it's been a very, very prolific program. It's resulted in over 2,000 publications in refereed journals and tons of press releases. Almost monthly you see a new press release from Sloan. And just as some examples, there's press releases on quasars, on different types of stars, on observations of interaction with black holes and their galaxy, the host galaxy, other types of stars, about how they map out the Milky Way. And here also on the right I show, just to give you an idea of the scale of it, think of what your handheld digital camera looks like. Here is our camera. This is the imaging camera next to Jim Gunn, who is basically the PI of the Sloan project. And below is an image taken from the imager of two colliding galaxies. Okay, so the next generation of Sloan, we worked in Sloan 2. That was about 3 years. And basically it was about all stars all the time. It was observing stars in the galaxy and exploding stars in nearby galaxies. And this is more closer to my heart. This is similar to the work I've done in the last 5 years, looking at a specific type of supernova and using them as distance measurements. I wasn't involved with this program. I was involved with something with the Hubble Space Telescope. But I will probably be using data from this program now in the next few years with a postdoc and a graduate student I've just hired who are in the audience today. Okay, so now we move on to Sloan 3. Now, basically, the Sloan 1 and 2 were the same imaging camera, the same spectrograph. Now, what was decided based on the interests of all the members of collaboration was to expand the program with 4 specific science interests in mind. At the same time this was happening, at the same time they were deciding to expand to the 3rd generation, the University of Utah here was expanding their astronomy department. So 2 things were happening in parallel. And given the perspective here, this was a perfect opportunity to get into the field with very good collaboration, with a very important survey, and at the same time you obtain access to the data, and also as a tool to recruit new faculty. Adam, Innes, Frank, and myself, who arrived in 2009. And in terms of funding this project, this was a joint effort between the Willard Eccles Foundation and the University of Utah. Okay, so I mentioned that the motivation in having a Sloan 3, a 3rd generation, was to focus on individual science topics. And in doing so, we developed specific cameras now with each science driver in mind. The one I'm involved with is the BOSS spectrograph, and that's for measuring, that's the closest related to the previous spectrograph. It's better, it's more sensitive and you can see further out with it. And the point here is to measure distance measurements using galaxies and quasars at high very distant quasars. two complementary programs are Segway and Apogee, and they're different methods of observing stars as tracers for the evolution of the Milky Way. And another camera is the MARVELS camera, which is looking for planets around stars. It's trying to look for new extrasolar planets. And these are all spectrographs at this point. There's no imaging camera envisioned for the next few years of the Sloan survey. So one of the science drivers of the Sloan-III is now to probe dark matter and galaxy formation. So that's what I'm going to focus on for the rest of this talk. I'm going to talk about two different probes of doing so. So basically the background here, there's a lot of observations out there, different methods for probing what material is out in the universe. And it turns out that about 4% of the universe is the stuff that we're made of, is electrons and protons, is atoms. So we have a pretty good understanding of that, not even completely, but we have a pretty good understanding. That's only 4%. The remaining 96% is dark matter and dark energy. Now, the dark matter part of it, we have a slightly better understanding of the dark matter than the dark energy. We know that dark matter behaves in similar ways to matter, at least in terms of gravity and the way it collapses under gravity. So the galaxies that form in our universe are going to follow, because they're interacting through gravity, they're going to follow the distribution of dark matter at the same time. So at the early universe, you have a fairly uniform distribution of dark matter, you have more clumpy spots and less clumpy spots. As time evolves, they become more and more diverse. Your clumps become clumpier and your voids become voidier. And the way of doing so is depending on how much dark matter there is, how much dark energy there is, and how it behaves. And here is a simulation, a computer simulation of how that clumping happens. And this is mapping out the evolution of dark matter since before any stars would have formed, up until today. So this is about the time when large objects are forming, like clusters of galaxies. And you can see in the simulation large voids here in the dark matter. You can see veins, and you can see knots. And by this, it kind of looks like a sponge. So we're using BOSS to try to observe the sponginess of the universe. And you're doing so by observing the galaxies that trace the sponge. So by spectroscopy, you basically get a direct measure of the 3D location of all these galaxies, and hence the sponginess of the galaxy, of the universe, sorry. And here is a map of those galaxies in 3 dimensions as observed from the first Sloan program. So again, just like in the last slide, you can see voids, veins, and knots. You see the same thing in the real data. And the exact way this distribution forms is a way of probing the properties of dark matter and dark energy. But because we're taking a huge sample of galaxies, we're going to have over 1.5 million galaxies, we're going to have 200,000 quasars. There's a lot of other science that be done with this in parallel. You have a large database of redshifts, you have a large database of spectroscopic properties of the galaxies. You get to see how galaxies differ, how they evolve, how they form. And Frank, who was mentioned earlier by Paolo, is actually responsible for sending me those simulations, not for creating them, but he put these slides together for me. And he's looking specifically at how the galaxies form and merge in the knots in the veins of the dark matter distribution. And he's doing it from a theoretical perspective. Adam, who's another new faculty arriving in 2009, he's interested in looking more at the individual galaxies in the BOSS spectrosample and looking for a strange alignments of multiple galaxies in the same line of sight. And I'll show you why that's interesting in a second here. So here's an example of one of these rare alignments. Now, what I see, because I've seen a lot of spectra, is a very well-defined in red elliptical galaxy spectrum. And I know by looking at that and identifying features that I'm very familiar with, like these two features right here, I know what effectively what the distance is to this, or I know what the redshift of this object is. Redshift is the parameter you really understand, but people think in distances, so sometimes I'm going to swap between the two, even though it's not quite correct. So I know the redshift of the galaxy, but what I see here also, above the red, which is not modeled by the red template, which is a very, very good match to the data, I see other lines that are out of whack. They don't appear to belong there. And what these are the mission lines from another galaxy that's sitting behind it. And in blue here is a template describing those emission lines in the background galaxy. So what I'm seeing here is a very distant galaxy with emission lines, a foreground galaxy that's very massive and red and elliptical. And I'm seeing them both, catching light from them both simultaneously, and I can't decouple the light. Now when you go and look at these objects in high resolution, like with Hubble Space Telescope, you can actually differentiate the two very well. And you can see that in many of the cases, you're not just getting projection along the side, they're not just lining up, but you're getting a serious lensing effect. The galaxy in the foreground, because it's so massive, it basically twists the light path. And it acts like the same way you would see looking through a distorted piece of glass. It distorts the galaxy behind it. And this is actually, there's a lot of information stored in here. This exact distortion as measured from Hubble Space Telescope, it depends on what the exact matter distribution is in the galaxy. So with a large sample of these objects, you can start modeling the mass distribution of dark matter within individual galaxies. And many of these were found in Sloan 1. We expect many more to be found in BOSS. We also expect many more distant ones. So this is going to give a pretty good probe on how galaxies are going to evolve with time. So you might have noticed as I'm doing this talk, I'm working from very distant objects I'm working in. Starting with cosmology, the evolution of dark matter, clumping a large structure, individual galaxies. This is all observations that were done with BOSS. But to get high resolution imaging and modeling of how galaxies are evolving, you need to go inside local galaxies. Well, for example, like our galaxy. That's the easiest. So BOSS gives a measure of the distant galaxies. The Apogee and Segway surveys within Sloan are going to get measures of Milky Way. And they do so in complementary ways. And one of the people in our department who just joined is Ines, and she's very interested in using these type of observations to model how the galaxy is evolving. So by looking at individual stars, you can actually follow the evolutionary history in different regions of the galaxy and try to map out the galactic evolution as a whole. One example of how this evolution progresses is from mergers with much smaller, fainter galaxies sitting outside the Milky Way and colliding. And you can track these mergers through both streams due to the interaction, and also through the properties of the stars, what type of metals are in the stars, how old the stars are. So you can actually see out in regions of the Milky Way, these streams of stars that have different properties than their neighbors, and this is an indication of merger activity. So those are observations that can be done with the Segway experiment. That's an optical spectrograph. It sees the same light that you can see with your naked eye. But what you can see with your naked eye, as you probably well know by looking at the Milky Way at night, does not cover everything in the sky. One of the biggest factors is dust lanes in the Milky Way. Dust lanes are great at blocking light in the optical, but in the infrared, as you go to longer and longer wavelengths, the light passes through the dust, and you can go observe this by using cameras with sensitivity to redder photons. So here's a picture of the Milky Way. You can see really nice dust lanes built into it. And by looking at these dusty regions with an infrared camera, an infrared spectrograph, you can look through it. It becomes transparent. This is an example looking in the region of Orion. You see a vastly different region of, vastly different structure in the sky than you would in the optical. And Apogee is the next camera. We expect to start taking data in about a year or so that will focus on infrared spectroscopy of the Milky Way and doing similar type of studies to what Segway did, but now focusing on regions near the galactic core that you can't see with Segway. Here's another really nice cross-section of a galaxy with dust lanes. So just to conclude, the Sloan and Sloan II programs have a very rich history in observational cosmology. We expect this rich history to continue with Sloan III, with 4 new science topics. And this variety of these science topics should keep all the faculty here at the University of Utah who are interested in Sloan III occupied for quite a few years.
My name is Pierre Sokolski. I'm the Dean of the College of Science, and just got off a plane from the Bay Area where I was visiting with the Associate Director of Lawrence Berkeley National Laboratory. And one of the first things he said to me is that, I hear you guys have a really dark site, so the word is out. I think we're going to get a lot of interest, both in terms of what this instrument can do now and in terms of what this might turn into if it looks as good as we think it looks now. This is really a great day for the Department of Physics and Astronomy, but it's actually a culmination of a momentum which began during a very difficult period in the Department of Physics history. Back in 2002-2003, I was chair of the physics department, and within a matter of 6 months or so, 7 faculty members came to my office and said, we're leaving. We got job offers here, there, everywhere. There wasn't any specific pattern as to why, but you know, it's if you're chair particularly, this is a terrible thing, but it's a difficult thing for the department. And one of the really positive things that happened is instead of falling apart, the department really came together and began to think and to plan how to rebuild. And one of the things that we talked about was moving into astronomy. I have to say, you know, partly because of the positive momentum of trying to build a program, and for other reasons, within 2 years we had rehired 8 faculty members. We're back to where we actually had one faculty member ahead of where we were. And then just recently we've hired 4 new astronomy faculty, and this year a total of about 7 new faculty have joined the physics department, to the point where faculty and chairs from other departments in the college are looking at me with some hostility, and my standard answer is Dave Kieda made me do it, so don't blame me. But really, I want to keep my remarks short because there's a lot of students here. You don't want to be between students and food. So I do want to just mention, though, that there's an overall context here. As great as this development has been, it is really part of the overall push in the College of Science for all 4 departments, chemistry, physics, biology, mathematics, to move into the top 20 slots in this country. I think it's doable. I think it's possible, and we're already approaching at those kinds of rankings on the national scale with a number of departments. And what we need to move up is exactly these kinds of programmatic efforts, where we start new programs, we bring in top faculty. And let me tell you, one of the wisest things that the upper administration of this university has done is not to freeze hiring during difficult times. The efficiency for putting out offers and getting a positive response is approaching 98%. So, and I think we're going to continue to see that in this coming year. So this is actually a great opportunity for the university to build programs. And I just want to mention, as an example of where the college is heading today, We just got word that a private donor has signed on a multi-million-dollar gift, which will allow us now to build the new chemistry building. And so that's, we have an NIH grant, we have a gift from a private donor. We will be breaking ground in about a year and a half for the extension that's back behind the Eyring building. Similarly, we are working very hard to build a Center for Science and Math Education. I think in a few months you'll be hearing news about that. There'll be a new, almost new building, or actually a reconfigured building, which will house innovative laboratories and teaching facilities for science and mathematics. It will also house a new facility for biology, the Cell Physiology and Genomics Center, which will have state-of-the-art equipment to really understand the mysteries of the cell. And if we're all keeping our fingers crossed, we might hear some really interesting and good news from the mathematics department in a few months as well. So College of Science is doing great. We all have these challenges from the state and from the economy, but in some ways this has been a great year for physics and astronomy and for the college as a whole. I congratulate the Department of Physics and Astronomy and all you guys, Wayne, who's been toiling quietly, blowing tires left and right, Dave, who's been very persistent, and of course to thank Steve and the Eccles and the Dumke Foundations for their faith and support, without which, of course, none of this would be possible right now. But I really do think this is a seed which is going to grow into a much bigger tree with what we see now. So thank you very much, and let's move on to the party.